So let us now take this expression that we derived and just try to calculate the delay of a path, because next class I would like to start the path delay optimization. Okay, I am saying this is 1x, 2x, I will say 4x, this is a NAND 2, this is a NOR 3, and ultimately I will drive it by a capacitance which is 64x. Okay. So what I want you to do is now calculate the delay of this path, D path, sorry. So D is simply summation of the independent delays. There are 4 delays here that I have to calculate. I will not calculate up to the last one, sorry, I will calculate only up to here, because otherwise I need to know the load there. Only three gates I want to calculate. Okay. So what we'll do is we will write down for, so this is I1, gate I2 and I3. Okay, I am going to now write a large table and we have to fill out these numbers for I1, I2, I3, C in, CL, load capacitance, logical effort, parasitic effort, no, I'll maybe say electrical effort first, then logical effort, parasitic effort, finally delay. So if for I1, what is the net input capacitance? How much? 3C, yes, right? What for I2, what is the net input capacitance? It is 4C, but I have said it's a 2x inverter. This 2 inside basically says it gives you the drive strength, which means I have sized it up by a factor of 2, right? Therefore, the net input capacitance that it would see is how much? 8C. What about I3? It's a NOR 3. So how much do you see? 7, 4, yeah. The NOR would normally present a capacitance of 7C, 1 from NMOS, 6 from PMOS, NOR 3. But I am upsizing by a factor of 4, and therefore I am getting a delay of how much? 28C. What about the load capacitance for each of these things? I1, it is 8C, right? I2, 28C. What about for I3? 192, 64 into 3x into 3C, you will get 192C. So what is the electrical effort H for each of these gates? Yeah? So it is simply 8 by 3 for this guy. This is 28 by 8, 7 by 2, and I3 is 192 by 28. What is that? 48 by 7. Huh? 48 by 7. Okay. Now what's the logical effort? G for I1, 1. I2, it is 4 by 3. I3, north 3, 7 by, yes, parasitic delay, effort, 1 for inverter, for I2, 2, for I3, 3, correct? So, can you now calculate the delay, which is basically GH plus P. What is the answer? For the inverter, 11 by 3, yeah. For I2, NAND 2, yeah, 20 by 3. And for NOR 3, yeah, 19, okay. Yeah, so you add this and you will be able to get an estimate for the path delay, okay. So you have to be careful only in the following case. What if I modified this circuit like this? This also is 2x. I add another NAND 2 parallelly, loading my inverter I1. Which of these numbers will now change? Huh? CL of I1. This will become plus 8C. What about C in of I2? Will that change or will that not change? So that will not change. That's the only thing you should be careful about, because remember that this C in, we are actually trying to capture the effect of the output resistance. That K that we got is how we wrote as C, we wrote it as C dUt by C unit. Now this gate is not contributing to charging this capacitance. That is just loading the previous stage, that's all. It does not contribute any current to charging the output load capacitance of gate I2. And therefore, it should not be considered when you are calculating the C in of the gate under test. You can only consider that branching thing when there is a load that you want to calculate. Okay, so here the only thing that will change is the load capacitance of I1 will become 16C instead of this thing. Therefore, the H for I1 will change. For I2, the H will remain the same. Okay, clear? Yeah? If it is connected, you mean like this? Huh? Then it's a different thing altogether. That's a different case altogether. Right now we are not considering this kind of a complicated circuit. I'll tell you how people handle these circuits later on. Okay, it's not part of the syllabus, but just for academic purposes I will tell you how they do it. Okay, basically you are saying there are multiple paths that are converging back to the same node. That is far more complex. Right now I am just talking about a single path. You start from a source node and then you can go out, you never come back. Clear? Any questions till now on logical effort, on delay calculation, path delay calculation? Because this is very important for us to proceed into the next part of this module. So anyway, you don't have to worry because these concepts will get reinforced again and again. We will keep coming back to this as we go on. So let me now start the most interesting problem that we would like to solve in digital circuit design, right? And that is basically called path delay optimization. In the previous example, I gave you the sizes. I said this was 1x, that was 2x, 4x and so on, and said calculate the delay. Now I am going to reverse the problem. I am going to tell you that there is a circuit that is sitting between an input node and an output node. I know the capacitance at the output node. I want you to find the sizes so that the delay between these two points will be minimum. Okay, so it's like this. I have the same, let me just take the same circuit. Okay, and let me put a, I'll add one more now. There is a load capacitance. Okay, I want to find the sizes of these gates which will minimize the delay between point A and point B. I want to minimize between A and B. Okay. So now clearly, if I went and chose my variables as, let's say, my variable was the size of the drive strength of the NAND gate, let me call it K1, this as K2, this as K3. Suppose I did that, then you already saw in the previous case, you have to put in a lot of effort to calculate the input and output capacitances because it depends on the topology of the gate, right? So that's not very useful. Not very useful and slightly more cumbersome, right? The delay expression we have derived is actually very, very compact and nice if you choose your variables correctly. So instead of choosing the drive strength as my variables, I am going to choose the capacitance here. Load capacitance X1, this capacitance X2 and this capacitance X3 as my variable. Okay, so let Xk be the input cap, and of course I need to assume that the first gate size is known. Let's assume that that is fixed. That is a minimum size gate, and this is just a reference inverter. So this is a 1x gate. Let Xk be the input cap of gate K plus 1. Okay, this is the input gate cap of the next gate. So you don't, make sure you don't count parasitic capacitances here. This is input gate cap of the next gate. It's just load capacitance. Those are my variables. Okay. So now what I can do is, I can write my delay expression for each of these gates like we did earlier, right? So I have gate I1, I2, I3 and I4. So I can write D1 as G1 into H1 plus P1. Of course here it's an inverter, so G1 is 1, P1 is 1 and so on. But in general I can write it as the delay of the kth stage is Gk into Hk plus Pk. Okay. What is H1 now? Yeah? Sorry? Huh? Yeah, so let's assume this is X naught. The input capacitance of the first gate is X naught. So H1 is X1 by X naught. What about HK therefore? X, it is just Xk by K minus 1. This is the advantage if we choose the capacitance itself as the variable. Then H's become very simple to evaluate. There is just ratio of these capacitances and I am done. Okay? So now what do I want to do? I want to find the following. I want to, the net delay is summation Gk Hk plus Pk. So I will write this out as summation Gk Hk plus summation Pk. Now this summation Pk is independent of my gate sizing. Parasitic delay is independent of gate sizing. So therefore this is a constant number. And I will call this as the path parasitic effort. Okay, so here is where I told you that it doesn't matter whether you do 7 RC or 6 RC or whatever it is for the NAND gate, contamination or propagation or whatever. It's a constant number that is not affected by my gate sizing problem. So when I do my minimization, that constant anyway goes out. You want to be more accurate, please be more accurate. It does not affect your gate sizing algorithm is all I was trying to tell you there. And therefore it's okay to make the approximation of only counting diffusion capacitances. Okay, so that's a constant number. Now what do I want to do? I want to minimize this objective function, summation Gk into Xk by Xk minus 1. Right, K going from 1 to how many ever gates there are in the circuit. I want to minimize this delay and my variables are Xk's. Okay, X0 is known, Xn is known. Now let us look at the nature of these terms. Okay, so let me look at the product Gk into Hk. Just let me look at this term and I will call it a term f, k equals 1 to n. This I can simply write as product of Gk 1 to n into product of Hk 1 to n. Now this is some product of logical efforts. Okay, so I will call this G, it's called path logical effort. Okay, now this guy is my path electrical effort. What is the path electrical effort? If you expand this and write it, it will simply become x1 by x0 into x2 by x1 into x3 by x2 xn by xn minus 1. So what happens? All the variables simply cancel out and you are only left with ratio of output load capacitance to input capacitance of that path. All the variables in between are gone. Okay, so therefore this I will simply write, I can just simply keep cancelling like this, and you will simply get as xn by x naught. Okay, and what is xn? It is basically this xn. My final load capacitance by input capacitance. Clear? Now you observe this term. I want to minimize the sum of, okay, let Fk equal to Gk into Hk. I want to minimize summation Fk, but the property of Fk is product of Fk is a constant, right? So what do you do now? You use arithmetic mean, geometric mean inequality, and you can solve. The left hand side is some form of the arithmetic mean, summation Fk by n, right? So I can say the following: summation Fk by n is greater than or equal to product of Fk whole power 1 by n. Right? This is nothing but Am greater than or equal to Gm inequality, and they will be the minimum will occur when each term is going to be equal. Okay. So what we'll do is we'll stop here. This is the outline of the proof. Next time we will complete this proof, solve a few examples, and then proceed with more interesting cases on the same lines. Thank you.